We usually think of water as, well, just the background, right? The stage where all the action of life happens. But what if it's way more than that? What if water isn't just a passive bystander, but the active, driving force that literally builds the molecules of life? Let's dive in and uncover the hidden architecture in a simple glass of water. So here's the central puzzle we have to solve. There's a fundamental rule of the universe, the second law of thermodynamics, which basically says that everything tends to get messier and more disordered over time. We call this entropy. And yet, life is this masterpiece of incredible order. So how do these fantastically complex molecules, like proteins and DNA, spontaneously fold themselves into perfect, precise shapes against this constant universal push towards chaos? Well, the secret, it turns out, isn't actually hidden deep inside the protein. It's in the humble water molecules that are all around it. See, they're not just spectators, they are the unseen architects, the guiding force that nudges and pushes a molecule like hemoglobin here into its final, perfect, functional shape. All right, so how on earth does water pull this off? Well, the first part of the answer lies in its unique personality. In chemistry, we call it polarity. And for our architect, this is the most important tool in the toolbox. It all boils down to the water molecule's lopsided shape. That big oxygen atom in the middle, it's kind of an electron hawk. It pulls the electrons it's supposed to be sharing with the hydrogens a little closer to its side. And this creates a tiny electrical imbalance. The oxygen side is a little bit negative, and the hydrogen side is a little bit positive. So every single water molecule acts like a tiny magnet. And when you have a whole bunch of these tiny magnets floating around, what do you think happens? They naturally start sticking to each other. The positive hydrogen of one molecule gets drawn to the negative oxygen of a neighbor. This little attraction is what we call a hydrogen bond, and this one simple connection is the master tool in our architect's kit. Now, here is the crucial detail. A single hydrogen bond is incredibly weak. I mean, look at these numbers. It's barely 5% as strong as the covalent bonds that hold the water molecule itself together. They're so weak they're constantly breaking and reforming in what scientists call a flickering cluster. It seems like a totally flimsy tool to build something as stable as life, right? But stick with me, because that weakness, that's its greatest strength. Okay, so we've got the tool, the hydrogen bond. But what's the driving force? What makes it all happen? Well, it's not an attraction. It's actually a powerful push. This is the famous hydrophobic effect, and it all comes back to that concept we mentioned earlier, entropy. Just look at what happens when you drop something nonpolar, like oil, into water. The water molecules can't form their nice hydrogen bond network with the oil, so instead they're forced to arrange themselves into this super-ordered cage-like structure all around the oily molecule. It's the only way they can maximize the bonds they can make with each other. And this forced order is a huge problem. This super-rigid cage goes against everything the universe stands for. Nature hates being forced into neat little boxes like this. It wants freedom. It wants randomness. It wants maximum entropy. So, and this is the really important part, it's not that the oil molecules are attracted to each other. Not at all. Water is pushing them together to save itself. It's kind of a selfish act. By squishing all the nonpolar bits into one blob, it minimizes the size of that ordered cage it has to build, and that frees up a ton of water molecules to go back to their happy, messy, high-entropy state. That is the hydrophobic effect. All right, so we have our two main players on the board, the gentle pull of hydrogen bonds and that massive entropy-driven hydrophobic push. Now for the fun part. Let's watch them work together to build life's molecular masterpieces. Take DNA, for example. That iconic double helix is held together almost entirely by those weak little hydrogen bonds. Any single one is nothing, but you get millions of them all zipped up between the base pairs, and suddenly you have an incredibly stable structure. It's strong enough to securely store our genetic code, but just weak enough to be unzipped for copying and reading. It's perfect. And you see this same dynamic duo in proteins like hemoglobin. It's brilliant. As a new protein chain is being made, that great hydrophobic push kicks in immediately. It forces all the greasy, nonpolar amino acids to bury themselves deep in the center, away from the water. Meanwhile, all the polar, water-loving amino acids are arranged on the surface, where they can happily form hydrogen bonds with the surrounding water, locking everything in place. So let's just pull this all together for a second. It's kind of mind-blowing when you really think about it. The massive, stable, unbelievably complex structures of life aren't built with superglue or powerful rigid bonds. They're built from the cumulative effect of a vast number of weak, temporary interactions, all conducted by the maestro, water. And while the hydrogen bonds and the hydrophobic effect are the superstars of the show, they're not working alone. They're part of a whole team. You've got your basic ionic attractions, opposites attract, and then there are these incredibly subtle van der Waals forces, which is just this faint attraction that happens anytime two atoms get close enough. But water is the medium, the environment that orchestrates all of them. And here's where the numbers just get wild. Because these bonds are always flickering, breaking one is easy, no big deal. But to completely unfold a protein or unzip DNA, you have to break all of them at the exact same instant. And the probability of that happening is practically zero. You only need about 5 to 20 of these little guys working in concert to create a structure that is, for all intents and purposes, rock solid. This isn't some new idea. The legendary chemist Linus Pauling recognized this profound truth over 80 years ago. He understood that it's not the strong covalent backbone of molecules that matters most, but the humble hydrogen bond, that fleeting electrostatic whisper that holds the real secrets to life's structure and function. So the next time you look at a glass of water, remember what you're really looking at. You're not just looking at a simple liquid. You're looking at the architect of life, a force that uses countless weak interactions to build immense stability. And get this, it leverages the universe's own relentless drive toward disorder to create the incredible order you see in every living thing. It leaves you with a pretty wild thought, doesn't it? Maybe true strength isn't about being rigid and unbreakable. Maybe it's built from weakness and driven by chaos.